Hello and welcome to Physical Attraction. This episode is called Frickin' Lasers. In the last few episodes, discussing the intricacies of magnetic fields and plasma instabilities, the triumphs and tragedies of the 1950s and 60s in magnetic confinement fusion research, it can be easy to forget that humans had already liberated vast quantities of energy from nuclear fusion on Earth. In fact, the first time it happened was on November the 1st, 1952, the Ivy Mike H-bomb test, which released so many new neutrons that two new elements, Einsteinium and fermium, were created above the wreckage of the atoll which was destroyed. In its place there was a crater 2 miles across and deep enough to hold a 17-storey building. But only 23% of its energy actually came from the intended fusion of the deuterium fuel, even if that is the equivalent of utterly annihilating 111 grams of matter. Or, in more relatable terms, it released enough energy to power the entire country of Mongolia for a year, or equivalent to the output of a standard 500 megawatt power station running continuously for 231 days. In other words, as early as 1952, humans were releasing enough thermonuclear power to compete with conventional power stations. The only problem was that the only feasible way to release it was a hydrogen bomb. You'll remember from our episodes on the hydrogen bomb, Edward Teller's attempts to develop it, and the eventual success of Ulam's design, the basic principles of how the bomb works. A primary fission nuclear bomb explodes with its standard chain reaction. The X-rays produced then travel down a tube into a chamber where they're used to very quickly compress a secondary pellet of deuterium-tritium fuel. Crucial to this, though, was focusing the X-rays onto the pellet in a completely symmetric way, which requires a careful design of the device. This then causes that capsule of fuel to rapidly implode, briefly reaching the incredibly high temperatures and densities, enough for the nuclei to overcome the electrostatic repulsion between the protons, and finally get close enough for the strong force to pull them together and for fusion to take place, releasing energy. In the episodes on Teller, we even talked about the various schemes, some more harebrained than others, to use nuclear bombs and hydrogen bombs for civilian engineering schemes, like carving out space for a port in Alaska, or cutting a new Suez Canal to resolve that rather tricky political crisis. Of course, you might ask, why not use the hydrogen bomb as a power source? After all, you've already devised a readily available way of liberating thermonuclear energy. You're already releasing that kind of power. The only problem is that it has this rather nasty tendency of destroying everything. In fact, it's very difficult to create nuclear bombs below a certain yield. The problem is that if you only have a very small amount of fissile material, you won't be able to cause a self-sustaining chain reaction. The neutrons will escape too quickly without producing that critical chain reaction. If you use control rods, as in a conventional fission power plant, then you can control the neutron flux to get a sustained constant burn. But then you won't produce a sufficient quantity of X-rays to allow you to compress a fuel pellet. Ideally, you would want to produce the powerful X-rays without the intense explosion that accompanies them. Then you could use the energy released in the ignition of the fuel capsule and its thermonuclear fusion reactions to drive a turbine, just like in a conventional power plant, but with thermonuclear fuel rather than fossil fuels or enriched uranium. This minimum feasible yield for a nuclear bomb was still far too explosive to use in this way. But this didn't stop Teller and his fellow inventive people from coming up with ideas. Project Pacer, for example, dreamed of detonating nuclear bombs in underground cavities filled with water. The nuclear bomb vaporizes the water into steam, which then drives turbines. Of course, the main attraction of this scheme for Teller was that it gave him an excuse to make ever more nuclear weapons. Early tests of Project Pacer demonstrated that it was little more than a very expensive way of making a radioactive hell pit filled with fissile material. Even if the scheme was successful, it still would have turned out to be 10 times more expensive than the conventional nuclear fission power plants that were being used at the time. Worse still, in some of the early tests, the cave system partially collapsed and radioactive steam was blown through rock vents far from where they'd intended. Finally, in 1975, the whole idea was more or less abandoned, although, amazingly, people have continued to look into it since by constructing artificial cavities underground that might be less prone to collapse. And the way fusion is going at the moment, even this might end up being cheaper than that. Nevertheless, people were still looking into what was slowly becoming known as inertial confinement fusion. You'll remember that we've talked about the Lawson criterion already, this thing that you need to have a net gain from fusion reactions. You need to have a high value for the heat of plasma times the density of plasma times the confinement time of the plasma. So the magnetic confinement strategy is to confine plasma for a very long time, perhaps ultimately many minutes at a time, and thus attain a self-sustaining fusion reaction with lower temperatures and densities. The inertial confinement strategy is more or less, hang the confinement time, that's just way too difficult. Just blast the damn thing so that it's incredibly hot and dense. After all, the plasma will remain close together for as long as it takes to be blown apart, if that makes sense. The inertial confinement time is the amount of time it takes for the capsule to explode. So if you're capable of achieving sufficient densities and temperatures during that time, you might just get enough fusion reactions taking place in your plasma to produce more energy than you put in, and this is called ignition. So effectively, you're not really bothering to confine the plasma at all, you're just explosively compressing it and hoping that it releases more energy than you put in to make that explosive compression. The plasma only stays together for as long as it takes to fly apart. Early calculations suggested that you could perhaps get more energy out than you put in with a relatively small amount of fuel, perhaps just a few milligrams or thousandths of a gram. It would only theoretically take a small amount of energy to ignite this fuel pellet, far less than you'd release by setting off a fission bomb. The fusion reactions would release about as much energy as burning a barrel of oil, easy enough for humans to harness without destroying the power plant every time you ignited the fuel. So you could even dream of using something like this to maybe power a large car or some other kind of device. You would just have something that would be able to ignite these fuel pellets and release the energy as a series of small explosions in a similar way to the internal combustion engine. The only problem then was how to ignite this tiny fuel capsule. As you're probably expecting already, the early theoretical calculations gave rise to a great deal of optimism. In the 1950s, early computers were simulating the implosion of a fuel capsule made of deuterium and tritium, and they seemed to suggest that delivering 5 megajoules of energy to the capsule could result in 50 megajoules being released, a gain of a factor of 10. Of course, we're not creating energy here, this energy just comes from the fusion of the particles in the fuel capsule. But the point is that in terms of fusion, it's a net gain, which is what all the tokamaks are trying to achieve, and were trying to achieve at the time. Later research on different capsule geometries showed that using a thin cylindrical shell around the fusion fuel would reduce the energy requirements even more. At the same time, 2 different branches of inertial confinement fusion were proposed. These are basically called direct drive and indirect drive. In direct drive, you compress the fuel pellet directly, causing it to implode. In indirect drive, you instead supply vast amounts of energy to a container for the fuel pellet. This container is called a Hohlraum. It's like a metal shell. In exactly the same way as the metal shell in a hydrogen bomb ensures that the fusion fuel is bathed in uniform X-rays from all sides, the same is supposed to happen in the Hohlraum. So you heat it to these really high temperatures, and then the capsule itself radiates nice symmetrical X-rays onto the inner pellet, causing it to implode and hopefully release energy. So now the only issue was heating that Hohlraum. Plenty of ideas were suggested. Carl Friedrich von Weizsäcker, along with Hans Bethe, was one of the many physicists who had worked out precisely how the sun's nuclear fusion worked. You may also remember him as one of the physicists who was taped in post-war recordings discussing the Nazi atomic bomb project and the reasons why it failed. At a meeting he hosted in the 1950s, an idea was discussed to ignite a thermonuclear fusion fuel capsule using shock waves from conventional explosives. If the shock waves could be made sufficiently symmetrical, they might be able to compress the capsule enough to result in fusion. Later, in 1964, the physicist Friedrich Winterberg suggested a scheme he called impact fusion. The capsule could be compressed using very small microparticles, which would be accelerated to 1,000 km per second and then slammed symmetrically into the fuel capsule. A few years after that, he was working with electrically charged ion and electron beams, which you could use to accelerate them very quickly using certain kinds of electrical circuits, and then slam them into the fusion fuel capsule. But these experiments were not capable of igniting the fuel. It was just impossible to accelerate these little particles symmetrically enough to really compress the fuel with that symmetry that it requires. It was the invention of the laser in the 1960s that really made inertial confinement fusion feasible. With lasers you could hope to achieve the kind of spatial and temporal coherence that you needed to drive this implosion. This means that, you are capable of controlling the space locations at which the sides of the capsule are hit and the time at which the sides of the capsule are hit, so that everything is roughly hit at the same time and you have a nice spherically symmetric implosion. Without that, you won't have ignition. Fiddling around with shockwaves or actual physical particles was just too difficult at this point. Not enough power, too much variability and turbulence in the way the energy was delivered to the shell. But lasers could provide a very powerful means of heating the fuel capsule, or even directly providing enough radiation that might implode the fuel capsule. All of this research began in the utmost secrecy for the various governments and scientists undertaking it. After all, here we're talking about exactly the same secrets behind the development of the hydrogen bomb. And it's obvious that if you have a set of lasers that can compress a small fuel capsule to burn like a barrel of oil maybe, releasing that sort of amount of energy, well, what would stop you from using the same apparatus with a much bigger fuel capsule and maybe a higher laser power to set off a nuclear explosion? But in 1972, in the spirit of scientific collaboration, one of the pioneers of inertial confinement fusion in the US, John Nuckolls, was allowed to publish a paper in Nature, carefully composed so as not to give away any military secrets, that outlined the basic idea behind inertial confinement fusion. He wrote, quote, "Hydrogen may be compressed to more than 10,000 times liquid density by an implosion system energized by a high-energy laser. The scheme makes possible efficient thermonuclear burn of small pellets of heavy hydrogen isotopes and makes feasible fusion power reactors using practical lasers." One key point that was identified by the Nature paper was why the laser was such a game changer. It's all to do with the pressure that can be achieved. The strength of chemical bonds prevents you from obtaining too much pressure just by physically pushing objects together. Eventually, those chemical bonds just snap under the pressure. Diamond, for example, can be crushed under a hydraulic press. Above around 1 million atmospheres, it's just not feasible to generate pressure by physically forcing objects together. Explosions can produce more pressure, as in the shockwaves that Winterberg was experimenting with, but of course they're also more difficult to control. In the case of lasers, however, you can take advantage of the fact that photons carry and transfer momentum. Yes, even when you turn the light on, the photons from the light bulb exert a small pressure on you. In fact, because the momentum carried by the photon is just its energy divided by the speed of light, the pressure due to radiation follows a beautifully simple formula. It's just the intensity of the light divided by the speed of light. So let's say you're 1 meter away from a 40-watt bulb, as I am more or less right now. That energy spreads out across a sphere with a surface of 4 pi r squared, giving around 3.2 watts per meter squared as the light intensity when it hits you. Divide by the speed of light, which is 3 times 10 to the 8 meters per second, and you get the pressure as around 10 to the minus 7 pascals, or newtons per meter squared. That's less than a trillionth of the pressure you're under all the time due to the atmosphere, so even if you filled the room with bright light bulbs, you won't notice the radiation pressure. However, interestingly, it is 100 times the atmospheric pressure on the Moon, which has virtually no atmosphere whatsoever. Now next time someone switches the lights on, you can go, "Gah! I'm feeling an additional pressure of 100 lunar atmospheres." Isn't Fermi estimation fun? Lasers offer a source of incredibly collimated, incredibly concentrated photons that can deliver an awful lot of energy, and hence momentum and pressure, to a very small spot. Remember, intensity is what counts for photon pressure, and not the total energy, because the intensity is like the number of photons hitting a meter squared per second. If you could deliver the 40-watt power of that light bulb to an area of 1 square nanometer, it would push down on that nanometer with a pressure comparable to that found at the centre of the Earth, over 1 million atmospheres. This is precisely the kind of thing you can do with lasers. Nuckolls' paper suggested that even the lasers of the day could blast the outer capsule with a pressure of 100 million atmospheres. The pulse need only last a nanosecond, yet it would be sufficiently intense to create immense pressures. The capsule would then implode inwards, the material of the capsule suddenly accelerated to a few thousandths of the speed of light, or 3,000 times the speed of sound, and this would then result in pressures of 1 trillion atmospheres, comparable to the pressure of the heart of the Sun, and hopefully nuclear fusion. Now the race was on to be the first to generate a fusion reaction this way. Both Russian and French scientists were reporting that they'd seen thermonuclear neutrons from pellets hit by lasers, but the imagination of the American public wasn't really captured until one of their own got involved. In the early 1970s, one of the people working on this was Kip Siegel. He founded a company, KMS Fusion, that worked towards getting inertial confinement fusion to work. This was pretty unusual, because most of the nuclear physics so far had been done purely under the watchful eyes of the government and the Atomic Energy Commission. Inertial confinement fusion in particular was not something that you wanted to be privately owned because, well, a major motivation for funding inertial confinement fusion is that everything you develop has dual purpose and may be useful for constructing limited yield nuclear weapons. If you had some symmetrical laser pulses that could ignite a capsule of fuel of your choosing, you might be able to make a nuclear bomb to order, where you can set the size and scale in advance. Weapons developers were interested in creating small-scale versions of nuclear explosions at any rate. They could provide a good way of testing the effects of particles and radiation from a nuclear explosion on military hardware. And of course, developing incredibly powerful lasers for weapons research has always been a fascination amongst military types, even though not always justified in use cases in the field. By 1974, and despite the protestations of the government, KMS was ready to make their big announcement. They too had seen thermonuclear neutrons. The New York Times called it a significant step towards the goal of nuclear fusion as an almost limitless source of energy. Siegel's result was really not that dissimilar to what Zeta had found, neutrons with a strong suggestion that they'd arisen from nuclear reactions, which was a far cry from claims of being able to generate power, as the magnetic confinement fusion people would tell you. But it put Lawrence Livermore Laboratory, which still boasted of associations with Edward Teller, to shame, because they hadn't achieved anything like it yet. It helped that Siegel was a good salesman, with a good story that lined up nicely with the American myth. Here was an entrepreneurial lone wolf, who might just be able to beat the Soviet and US governments to the target. He believed in what he called the lessons of the Cavendish Laboratory in Cambridge, England, where a few bright people out-invented the world for a long time with wires and chewing gum. And he managed to attract several of the best and brightest US physicists to the startup company. The fact that private industry was starting to take an interest in fusion was a good sign to the public, who by now had heard the fusion in 10 years line for 20 years. If there was a private industry involved, then maybe the experts were believing that fusion reactors could be profitable and just around the corner, a viable and imminent source of energy. The government might be able to invest in blue sky research, but companies need results, at least so the thinking went. And although few serious fusion experts would have believed the timescales that Siegel was proposing for commercialising fusion, the mere fact that he was suggesting it was possible put pressure on the magnetic confinement programs and the government to make similar promises. Of course, it came at a great time to be involved in energy research in the US. The early 1970s saw the oil crisis, where OPEC members cut off oil supplies to the US and the price of gasoline skyrocketed. And this motivated a huge increase in investment for alternative sources of energy. From a geopolitical point of view, the US realised that it couldn't depend on OPEC or foreign oil imports. This was the decade that the Department of Energy was created. Solar panels for the first time were developed for use as power sources on Earth rather than just niche, space-based applications. In fact, if you look at any graph of solar cell efficiency development, it really starts to take off in the 1970s. Wind turbines were further developed and deployed. This took place across the US and Europe, every nation affected by OPEC's decision, and in many ways the 1970s was the birth of renewable energy aside from hydroelectric power, as a serious force that people could dream would one day take over. Incidentally, it kind of drives me up the wall that one of the greatest times for funding for renewable energy projects owed to OPEC turning off the tap. The fact that fossil fuels are finite and will run out and that they destroy the environment and cause climate change should be enough to motivate this level of effort and interest the entire time. The fact that depending on oil-rich economies is sometimes geopolitically bad should be somewhere down on the list of motivating factors for developing new renewable and clean sources of energy. But I suppose everyone who wants humanity to explore the stars has to deal with the same idea, that a great deal of spaceflight development arose out of the Cold War competition and not due to some grand vision of what the species can achieve. We might be smart, but we think in the short term, and we're not wise. It was in this milieu of trying to reduce dependence on foreign oil that a great deal of additional investment into nuclear energy, including fusion, took place. The magnetic confinement fusion budget skyrocketed from $30 million a year to $300 million a year, in the space of just 7 years. The budget for inertial confinement fusion skyrocketed from nil to $200 million a year by the end of the 1970s. Sadly for Kip Siegel, he wouldn't live to see the huge inertial confinement fusion projects that he had helped to trigger. In the midst of testifying about the promise of laser fusion to Congress, he suffered a stroke and died shortly afterwards. His company, KMS, limped along until 1990, and if you're interested in its history, you can find a testimonial of someone who worked there on the Kip Siegel page at Fusion for Freedom. Little did they know that their idea, to drive inertial confinement fusion with infrared lasers, would ultimately prove unworkable. The catchphrase used internally in the company, online by 79, proved to be just another over-optimistic fusion estimate. Yet Siegel was a pioneer in several ways, both in demonstrating that inertial confinement fusion could produce thermonuclear reactions with lasers, and also in paving the way for future entrepreneurs to try their hand at fusion themselves. While it's true that previously companies with big R&D sectors like General Electric and General Atomic had invested some in fusion programs over the years and decades, none of them had done so publicly as private startup enterprises with an official stated aim of commercializing fusion power. We will have plenty more to say about the private companies that have attempted, and are currently attempting, to circumvent the international collaborative efforts and develop commercial fusion before anyone else manages it. Next time, though, we'll talk about the early big government attempts at laser and inertial confinement fusion, Project Janus and Project Shiva. Thank you for listening to this episode of Physical Attraction. As ever, you can find everything you want to know about us on the website at www.physicspodcast.com. There you'll find a contact form where you can send any praise, feedback, criticism, comments, questions, concerns. I read them all and reply to the ones that aren't too batty. You can also follow us on Twitter at PhysicsPod. You can find us on the Facebook page at Physical Attraction. You can contact us in all sorts of different ways using these media. You can donate to the show using PayPal or by subscribing to our Patreon, but the best thing you can do to support us is always to tell as many of your friends about the show as you possibly can. Until next time then, take care.